This work is about. I'm quite loud. I don't think I need this. Okay. Well, this work is about additive manufacturing of titanium samples, or as some of you know it, as 3D printing. What we did in this research was to evaluate the effect of the notch geometry or geometric discontinuities on the samples produced by additive manufacturing. The samples were made by the selective laser melting method, SLM, which is a powder bed method that produces the samples layer by layer. And in each layer, the laser will melt the new powder layer, and at the end you will have your final geometries. This method has been used for different materials, metallic materials like copper, tool steel, cobalt, chrome, titanium, tungsten, aluminum, stainless steel, and gold. So far, the main concern of researchers working on additive manufacturing has been on the quality of the product and not on the design of it. As you can see, new components, complex components made by additive manufacturing has complex geometries, and they are mainly made in a single part. Here you can see some examples. But the main concern of our group is topology optimization, because we are doing it in Untitled, and there is a group called Revolve that they are working on topology optimization for producing different components for race car to have the lightest race car ever. As you can see in this component, there are so many different types of geometrical discontinuities, and they are considered as stress razors. So what you have around this notch, or the mechanical behavior of this notch, is dependent on the geometry first and on the production method, and you cannot consider it as an isotropic material due to some defects inside the material and also the surface condition. But we have tried to start a research by considering just some simple cases. So 3 different types of samples were produced by SLM. Smooth specimen with a stress concentration factor of 1.05, which is almost 1. And 2 notch component, V-notch samples, which are blunt V-notch, and semicircular notch samples. 12 samples were produced for each geometry, and heat treatment was conducted on each sample to release the residual stresses. Here you can see some details about the fabrication, like the process parameters for manufacturing the sample. But mostly, we are not defining these parameters. These parameters are suggested by the company who was providing the machine. But just to be nice, I put them here. The samples were prepared for micromechanical analysis and etched, and afterward you can see the microstructure of the sample here. Due to the low contrast, probably it's not too clear, but you can see that the grain boundaries are elongated along the printed direction, which is Z here. And on the surface up here, in the XY plane, they have almost circular shape. Here you can see some other microstructural pictures of the samples. What you see is the primary beta grains in the sample during fabrication, but due to really fast cooling of the samples while when you're producing them, the main phase that was observed in the samples is the martensite phase. And you can see these dendrites, which is a combination of alpha prime, alpha double prime, and beta prime in the material. If you compare it to the casted sample, here you can see clear existence of alpha and beta phases. which is quite a different behavior compared to the additive manufacture samples. We are expecting to have more ductile behavior for these casted specimens because beta phase exists in it. So first of all, some smooth specimens were tested under static loading to get the static properties. As you can see, this one is the casted sample. And the usual failure mode in the casted titanium sample is a combination of ductile and brittle-like failure. It's not brittle, but it's brittle-like failure. The ductile part is in the core of the material, and the brittle part is the surrounding of the ductile part. The same test was done on 3D printed samples. As you can see, that ductile part doesn't exist here. It's all brittle. But the brittle behavior in titanium is not cleavage facets. No, it's dimples, but shallow dimples compared to the deep dimples that you see in ductile failure. Afterward, fatigue tests were conducted on casted specimens. Here you can see the results for smooth sample, semicircular sample, and lumpy notch samples. As it is usually expected, fatigue strength for notch specimen was lower. The same test was conducted on additive manufacture samples. What we observed was that the fatigue strength again was lower for the notch specimen, and the highest fatigue strength was for the smooth sample, which is not something exceptional. Here you can easily compare the values. The value of the fatigue strength for semicircular sample in the wrought material is a bit higher than smooth sample, which is a bit strange, but that's due to the experiments that we conducted. We need to do more experiments close to the fatigue limit to get that accurate value. However, the main concept of this work was additive manufacture sample. As you can see, the fatigue strength for smooth sample and also for notch specimen that were made by 3D printing were lower than the samples which were casted. It can be due to a lot of reasons. First of all, the surface condition. The additive manufacture samples were not machined afterward. They were having the roughness equal to 60 micrometer, which is considerably higher than 25 and 20 micrometer for the machine samples. Besides that, some internal defects exist in the case of 3D printed samples that they can result in this lower fatigue behavior. Well, smooth specimen made by additive manufacturing were observed under CM microscope. As you can see, the fatigue initiation sites were the surface defects mainly, and also in some cases also internal defects. The same observation were obtained for the notch samples. As you can see, clear defects on the surface act as pre-crack or pre-notch, and that results in lower fatigue load in this case. But about internal defects. Two categories of internal defects were observed, which was first lack of penetration, which I have seen in several cases in the publications mentioned as cleavage facet. It's not cleavage facet, this is lack of penetration. So between two layers of printing, there was a thin layer of air. Or in some cases, it's too, the gap is too much that you can see also unmolten particles inside the material, surrounded by the void. Also, the surface condition, you can see one of the disadvantages of 3D printing is the defects close to the surface. That's why a lot of people usually machine the samples after 3D printing. So they can remove these defects close to the surface. And here you can see that the crack has started not from the notch tip, but from a defect close to the notch tip, which can make it a bit harder to use classical models for predicting the fatigue behavior of this material. But let's go background. There is a method called SED, strain energy density, that was previously used for predicting the static behavior of the material. As you can see, this method considered the average value of SED as a parameter in a control volume around the notch tip or crack tip, and when this value reaches a critical value, the sample will fracture or fail. The radius of control volume can be obtained by mechanical parameters of the material, and the critical SED is also can be obtained by ultimate strain and elastic measures. This has been done before. Then Lazarin extended this method that he proposed again for fatigue loading. The problem for fatigue assessment is that when you plot stress versus life, you get different curves for notch specimen and smooth specimen. So Lazarin suggested to use SED instead of stress. So instead of having, for example, in this case, 3 curves for 3 different geometries, you get a unique curve, or called master curve, which consists all different geometry. In this case, instead of doing the test for different type of geometries, different type of notch, you just do the test on the smooth specimen, and you can predict the fatigue behavior of the notch component. Whatever is the geometry, it doesn't matter. Which is really important in 3D printed samples optimized samples, geometrical optimized samples. You have so many different types of notch, and it's impossible to do 20 fatigue tests for each notch to be able to predict fatigue behavior. So here, using SED, you can do test on only smooth specimen and be able to predict the fatigue behavior of the rest of the geometries. I should explain it a bit faster. These are the basic knowledge of SED and the formulation that we can get from the work conducted by Filippo Berto et al., which is published in Fatigue and Fracture of Engineering Material and Structure. I passed this fast because the other method to get SED value is FEM. So you don't need to use this analytical method. You can also simply get the SED values from Abacus, ANSYS, or any other FEM softwares, which is quite easier than calculating it by analytical formulations. These are related to the analytical formulation and experimental validation. So what we did was to use this SED method for the first time for the additive manufacture samples, and as you can see, a unit curve was obtained for 3 different geometries, which was smooth sample, semicircular, and V-notch specimens. This one is the casted sample, and the next one is the as-built sample. And with this method, we can be able to predict the fatigue behavior of the other geometries of additive manufacture components. Due to the lack of time, I have to finish my presentation. Thank you very much.